I'm Alex, and today I want to introduce you to our protocol LogPicker. At the beginning, let's take a short look on how secure communication works on the web nowadays. So, in the year 2020, in January, about 95% of all page loads in the browser Chrome were served using HTTPS. And the certificates needed for HTTPS are created by certificate authorities, short CAs. And they are needed for binding a public key to a domain. So the procedure on how the certificates are issued and what exactly the requirements are for the acceptance of the certificates by browsers are defined in the CA browser forum. Consequently, the number of illicit certificates creation is increasing. So just here to give you a short overview, we had, for example, WooSign, who had several issues from backdating certificates or to not reporting known incidents, or TurkTrust, who issued intermediate certificates that normally should be regular SSL certificates, which is a big problem, or the Malaysian DigiCert, they issued certificates with weaker keys. So, however, most of these incidents happened due to the violations of the browser forum guidelines, or due to security vulnerabilities or technical issues. This means that attacks were probably not intended. However, let's assume a sufficient strong attacker who is able to misuse the web PKI for, let's say, surveillance reasons. This kind of attack is known HTTPS interception. And for this, the attacker must obtain something that we call a rogue certificate, which is a certificate for a domain that the attacker does not own. And several attempts for HTTPS interceptions were already documented. Especially for attempts by governments with, let's say, a weaker commitment to democracy. So the newest case is, for example, Mauritius. Google and Mozilla took action to protect their browser's users against this attack. But we wonder, why should a strong attacker like a government stop here? Let's get a closer look into the details of this attack scenario. So in 2007, Aumann and Lindell introduced the covert adversary attacking model. And the main characteristic of this attacker is that he only attacks if he can stay undetected with his attack, even after the attack is finished. And Sogin and Stam introduced in 2010 a suitable attack scenario, which is called the compelled certificate creation. For this scenario, it needs a strong attacker who is able to compel a CA to omit the domain ownership check. And this way, the attacker can obtain a rogue certificate. So our scenario means that we have an attacker who succeeds in creating a rogue certificate that remains unnoticed by its legitimate domain owner. Well, the mitigation attempt against this kind of malicious CAs is certificate transparency, and the pre-work on it began by Laurie Caspar-Langley in about 2012. So the goal was to make illicit certificate creations impossible without the domain owner's knowledge. And this was achieved mainly by forcing CAs to publish their certificate issuances in public logs. So just a short primer on the protocol of certificate transparency. At the bottom we have the CA who wants its certificate to be accepted by a CT-capable browser. So it needs a proof that it submitted its certificate into a public CT log. That means it sends its certificate, this red thing here, to any favorable CT log. Trusted by the target browser. And the CT log must then include the certificate into its Merkle tree without the MMD, which is the minimum merge delay. It's about 24 hours. However, the CT log responds immediately with an SCT, which is a signed promise on I will include your certificate into my Merkle tree in the next 24 hours. And the CA can now take the certificate, which is newly created, and accompanied by the SCT log, send it to the domain owner. And the domain owner can then deploy her website or whatever with HTTPS. Certificate transparency introduces two new entities into the web PKI. First are the auditors, mostly third party, and they check whether CT logs comply with this SCT, the signed promise, and some CA browser forum requirements on CT logs. It means this auditing check is domain independent. The other party are the monitors at the bottom in this picture, and the monitors mainly check for a specific domain whether the CA always did the domain ownership check. So that means only valid certificate issuances has been logged in the CT logs. So this is domain dependent, and however, domain owners must manually opt into monitoring, so it's mostly used for high-value domains. However, we think that certificate transparency is still vulnerable, and at the moment, each CT log that is trusted by the Chrome browser is also belongs to a CA vendor. So we assume that attacking a CT log is equal to attacking a CA. And the first compromise of a CT log happened in 2020 due to a salt vulnerability, I think. Oh, and well, fun fact, yesterday I heard about another CT log issue, which happened due to a random bit flip, I think. Well, so we assume a collaboration attack by a malicious CT log and malicious CA to be realistic. And this scenario already was considered in the CT threat model document to be an open problem. Because you had introduced a low probability but high impact scenario, which is mainly motivated by political or commercial or social reasons, which is kind of the same attack we're talking about now. And for this kind of compelled certificate creation attack, a malicious log must create a split view attack. A short primer on split views. The log deploys two different views. The first one is only served to monitors, which you can see here on this picture, and the red certificate, which the CA created previously, is not included in this view. So the domain owner won't detect a rogue certificate, so it remains undetected for him. The other view is served only to auditors, and as you can see on the picture, it includes the rogue certificate. And this means that it's not a problem for auditors because they are unaware of which domain belongs to who, so they won't see the violation of the CA browser forum requirements, and this attack remains also undetected. A mitigation attempt for this attack is gossip, certificate transparency gossip, and it kind of involves each participant of the WebPKI into this auditing process of the log in charge. And it's something like web servers talks to auditors, and clients talks to web servers, and clients talk to auditors and breach their browser history, by the way. And kind of everyone is talking to each other. I just kind of lost the track about that. So due to the complexity and many other reasons, gossip is still a draft since I think 2015 and will probably stay so. Anyway, why not solving this issue by introducing some new trusted entities into the WebPKI? Well, because it won't help, as already warned by one of CT's inventor, Ben Lowry. So instead, our work proposed another approach. The protocol, which we called LogPicker, extends the current certificate transparency procedure by mainly involving more witnesses into the certificate issuance process and allowed automated auditing of the CT logs. Let's take a short look on the Desiderata for our protocol. So we have security and design goals. For the security goals, we want to mitigate collaboration attacks, which we talked about earlier. So, and since we support CT's approach for making certificate issuance publicly visible, we want to enhance this approach by mostly involving more witnesses into it. And the witnesses should also be able to prove their participation in this certificate issuance. And in addition, we want to try to involve monitors earlier into the certificate issuance process. Well, but to get back to the design goals, we don't want any user data to be involved in this procedure. And the same is for web servers, because we think that web servers tend to be outdated, so they shouldn't be involved in any kind of WebPKI changes. In addition, we believe that incremental deployability by certificate transparency was one of the most of the successes of CT, and we want to follow this approach as well. And at last, we don't want to introduce any new trusted entities into the WebPKI because we think it's quite complex already. Okay, to give you a very rough overview on our protocol and without going too much into detail, this is how it looks like. So at the bottom we still have the CA who creates the certificates. But this time it does not submit a certificate to any favorable CT lock, but instead to a pool of locks, many locks. And this pool of locks is formed based on the target browser's trusted CT list, which already exists at the moment. So this pool collaboratively selects a lock at random among them, and the selection's outcome isn't predictable as long as at least one honest lock was among them. On commit, each of those locks from the pool signs the proof that is collected in kind of a multi-signatures, and we call this proof the LPP, the LogPicker proof, and it can be used to prove the participation on the execution of LogPicker for one specific domain. Well, during execution, at multiple points, at least one honest lock can notify the monitor about the current execution for its domain. So the monitor is involved earlier into the issuance process. And the LPP can be attached to the certificate, the same way as it's the case with the SCT nowadays. So LogPicker-capable browser can enforce the use of LogPicker by enforcing each certificate to be accompanied by an LPP. And after the MMD, this 24 hours promise, each witness which are also CT logs in the pool, can automatically audit the lock in charge for logging the certificate. Well, let's take another look into the achievements. In our security goals, the attacker cannot forge the selection of the malicious lock which it wants to collaborate to because it's random. And participants of the lock pool serves as additional witnesses into the certificate issuance process. Each witness signs the outcome of this LogPicker execution, and during the execution the monitor can be notified about the certificate issuance attempt, no matter on whether it worked or not. The user's private data has no part in our protocol, and the same is also for web servers. They are not involved by this kind of changes. LogPicker's mitigation does not need a kind of a flag day for the changeover. It's only for the web servers. The next time they will deploy a new certificate, they will get a LogPicker capable certificate. And at last, LogPicker only reuses the current entities of the web PKI, which are the CAs, the CT logs, which at the same time are the auditors, and the monitor. And in addition, LogPicker assumes each participant in the protocol's execution to be Byzantine but one, which we call the one honest lock assumption. So, to the additional paper contributions, LogPicker uses a lot of crypto, which is kind of this multi-signatures or distributed randomness procedure, and these are explained further in the paper. In addition, it explains some details on our security and design goals of the protocol. Then we analyzed the overall correctness probability of the web PKI. First, what we called the LogPicker-based PKI, and then we compare it to the CA-based PKI's correctness probability, CT-based, and the gossip-based PKI. Further, we discuss how the current CT policies can be adopted to LogPicker and which kind of changes are needed. And at last, we deployed a prototype simulation of the LogPicker protocol, and it shows that LogPicker is scalable and can handle the current load of the web. And of course, we have a lot of work to do now. So we need first a procedure on how exactly can we include the monitors during the LogPicker execution. And then we need LogPicker clients that are also able to perform this interlog auditing, which is this automated auditing by the logs of the pool. And then at several parts of the protocol, protocol aborts can occur. For example, because one of the logs in the pool detect another Byzantine log, which is, for example, malicious. And the protocol at the moment is aborted. So we have to think about how can we handle this kind of protocol aborts, or maybe how can we reduce them either. And at the end, we all know that certificate revocation is still a nightmare on the web. So maybe it's anyhow possible to include certificate revocation into the LogPicker procedures. Well, thank you for listening, and I'm open to your questions now.